Welcome back to Honors Calculus. In this video, as it says above me, we're going to be talking about the real numbers. Last time we were talking about some of the other sets of numbers, and I mentioned that after you get through the natural numbers and the integers and the rational numbers, most algebra teachers give this hand-waving argument of there's a bunch of numbers that aren't rational, that can't be written as fractions, and we need something to do with them. And we call those numbers the real numbers. And that's very unsatisfying. So I want to try to start towards correcting that today. The very first thing I want to do is give you the correct definition of the real numbers, and then talk about what the heck it means. And oops, I should get my head out of the way so that I'm not blocking this definition. The real numbers, which are denoted using a blackboard bold R, or I guess to be more technically correct, this should be the set of real numbers, are the unique, complete, ordered field such that the rational numbers Q are a subset of R. Right? Unique hopefully makes sense. There's exactly one set that satisfies this condition. Q is a subset of R. Again, should make sense. We talked about subsets last time. So the interesting points here are complete, ordered field. Today, I'm going to talk about what it means to be a field and what it means for a field to be ordered. And it turns out that just having an ordered field is enough for a lot of what we want to do with the real numbers. So we will stop at having an ordered field. It will be busy enough that it's a good stopping point. And then in a couple of weeks, we'll come back and we'll establish what it means for this ordered field to be complete, and we'll get a couple of other nice properties. Right? So ordered and field are the rules for today. Right? A field is a set that we denote using a blackboard bold letter. I'm going to use F to be generic. So a set equipped with two operations, one of which we will denote using a dot, and the other one we will denote using a plus sign. Those are going to be multiplication and addition. Nothing weird is going to happen there, such that each of the following hold true. And before I get into my discussion of a field, I do want to point out that the real numbers will form a field. The rational numbers also happen to form a field. So that's one of the reasons that that idea of complete is going to be so important, because the rational numbers are themselves an ordered field. So having completeness doesn't really, or until we have completeness, it doesn't really differentiate anything. All right, but there are several properties of a field. There are specifically 10 of them. And let's go through and talk about each one. These should all be things that you are familiar with. Sometimes the vocabulary is a little bit new, but the concepts should be familiar. Let's use words for that. Our field, the real numbers or the rational numbers, is what's called closed under both addition and multiplication. For any two elements, x and y, in that field, the sum, x plus y, is in the field, and the product, x times y, is also in that field. All right, so that's what closure means. A set is closed if whenever you perform the operation, the result is still in the, still in the field. And for addition and multiplication, all of our sets are closed, right? The natural numbers are closed under addition and multiplication. The integers, the rationals, and the reals, they're all closed under both addition and multiplication, so that doesn't differentiate anything just yet. Addition and multiplication are both commutative. Like I said, these should all be things you're familiar with. So for any two elements, x and y, in that field, x plus y has to be equal to y plus x, and x times y has to be equal to y times x. That's the commutative property. Addition and multiplication are both associative. And associative, remember, is the rule where if you have multiple of those things, everything works out fine, no matter what order you perform addition and multiplication. Once again, all of the sets of numbers are commutative. They are all associative. Some numbering systems number those as two separate properties: commutative for addition, commutative for multiplication, associative for addition, associative for multiplication, as four properties instead of just two of them. Right? We have to have a unique identity for addition called 0. And then we have an additive inverse. And this is where the natural numbers fail, because additive inverses are the negative of a number. And so we are left with the integers, rationals, and reals as satisfying these properties. Now that we're talking about an identity and an inverse, it probably isn't too much of a shock to you that we're going to go on to a multiplicative. Right? The number 1, so that 1 times anything is that thing. And then for any element other than 0, there is a multiplicative inverse. The thing you probably know of as the reciprocal, which we'll denote as x raised to the negative first power. And if you multiply a number times its reciprocal, you get 1. Nothing crazy going on there. Oh, that's where I missed one. I gave 2 number 5s. That was silly of me. Wait a second. There's supposed to be 8 of these, and I only got 7 because there were 2 number 5s. And then the last thing is the distributive property. Again, something you are very familiar with. Whether or not you think about the names may have been a different thing, but you should be familiar with all of those properties. And that's what it means to be a field. So again, the rational numbers form a field. The real numbers also form a field. The natural numbers do not because they don't have an additive inverse. And the integers do not because they don't have a multiplicative inverse. But we get all those things, and then we have a field. Right? A couple of nice properties of numbers that you should be familiar with fall out just from that definition. let F be any field and pick an element X in that field. Multiplying that thing times 0 gives you 0. Right? This is something that you are very familiar with. Multiplying something times 0, the result is 0. The fascinating thing here is that that's a natural property of a field. And as long as you have those properties, commutative, associative, identities, inverses, and the distributive property, that forces this to be the case. And in order to prove that, actually, sorry, I was going to write out a proof, but as I'm thinking about it, let's do a simpler proof instead. All right, in order to prove that, let's note that 0 plus 0 is equal to 0. So 0 times x is the same thing as x times 0 by the commutative property, which is equal to x times 0 plus 0 by the substitution there, right? 0 plus 0 is equal to 0, so replace 0 with 0 plus 0 right there. Let's distribute that x and then rewrite that in a way that makes a little bit more sense. Now remember, you know and I know that if you multiply anything times 0, you get 0. But that's what we're trying to prove, and until we prove that, we can't just assume that. So we don't know that 0 times x is 0 just yet. But we do know that it's a number in the field because the field is closed under multiplication, and 0 and x are both elements of the field, so their product has to be another element of the field. Right, so 0 times x is in the field by the closure property, and anything in the field has an additive inverse, which we write as the opposite of 0x. Again, you know and I know that this is really just 0, but we haven't established that yet, so we're going to go through all the motions. So I should be able to add the opposite of 0x to both sides of the equation. And then, using the associative property, I can choose to evaluate that bit first. And any number plus its opposite is 0. That's the definition of the inverse. And then any number plus 0 is that number. That's the definition of the identity property. And so we've established that 0 times anything is equal to 0, and that must be true for anything that follows the axioms of a field, whether that is actually the number 0 or if it's something completely different. For those of you who are going to continue onward in your study of mathematics, you may eventually take a course in linear algebra where you start learning about vectors. You may have learned about some basic ideas of vectors in your physics courses up to this point. You may also start studying matrices and some of the other objects, the rotational groups, which are entirely geometric in their nature. But we can still establish an idea of 0 for all of those things, which doesn't look like the number 0, and yet still has this property because we know that that thing is a field and it satisfies these requirements, and that's all that it takes. So kind of a fascinating idea there. I know, once again, a long way to go for something that you're already familiar with, but that's what mathematical proof is all about. We don't just care about what is true in mathematics, we care about why is that true in mathematics. Up next, I'm going to look at one more idea of real numbers, one more thing to prove. And again, something that you've used very frequently in your mathematical career up to now and may or may not have thought of. That thing is the zero product rule. Right? Whether or not you know it by name, I am certain that you know what this is. Let x and y be elements of a field such that their product x times y is equal to 0. Then x equals 0, y equals 0, or possibly both. And I like this proof because it lets me play around a little bit with the logic here. If y is equal to 0, then we're done. If y is equal to 0, then either y is equal to 0 or both x and y are equal to 0, and we're done. So let's assume that y is non-zero. If y is not 0, then the only way to make this work is for x to be 0. So we want to try to prove that x must be 0. And it turns out that that's actually fairly straightforward to do. Right? But again, why can't I just say, assume y is non-zero? Because if y was 0, this would be a very boring proof because we would just say, okay, if y is 0, then we've satisfied the theorem. But if we assume that y is non-zero, so that we have to work a little bit harder, that means that there is a multiplicative inverse, the reciprocal of y, somewhere in the field. And so if x times y is equal to 0, then that means that x times y inverse is equal to 0 times y inverse. And we just established that if you multiply anything times 0, you get 0. So over here, if you multiply a number times its reciprocal, you get 1. That's the property of inverse. And over here, that's the result from the previous theorem. And then finally, if you multiply anything times 1, you get that thing back. So we've established that if the second thing is not 0, the first thing has to be 0. And whether the first thing is 0 or not, the second thing can be 0. All right. The important thing, the real idea of the zero product rule is that x and y cannot both be non-zero, and we've established that. All right, but now we have the zero product rule, and we'll be able to use it a little bit later on if we so desire. But let's move on from our discussion of fields I forgot something very important in this definition. In order to talk about a field, I'm going to have to name it. Shouldn't come as a surprise to you that I'm going to name this field using a Blackboard bold F. So the idea of an ordered field is the idea of an inequality. An ordered field is a tool on which I can establish an inequality relationship. And an inequality relationship satisfies 4 properties, or an ordered field satisfies 4 properties. An inequality actually doesn't need the first one, but that's specifically for a field. Any inequality will satisfy the last 3. The connex property says that everything is ordered. For any 2 elements, x and y, in the field, x is less than y, or y is less than x. There is a way to relate those two one way or the other. The reflexive property you should be familiar with. We named that when we were talking about equality. X is always less than or equal to itself. next we have an anti-symmetric property. Right? So we had a symmetric property when we were talking about equality. An anti-symmetric property should be opposite that somehow or another. Right? The anti-symmetric property, if x is less than or equal to y and y is less than or equal to x, then x is equal to y. Oops. And then the transitive property, again, something we've already seen. If x is less than or equal to y and y is less than or equal to z, then x is less than or equal to z. All right. So convex, not a name that you run across very often, but it is a property that has a name, so might as well mention it. Convex is very similar to closed. Everything is related one way or another in the field. Reflexive property, everything is related to itself. Anti-symmetric. If the relation works in either direction, that means that the things that you're looking at are the same thing. If you think about it, the anti-symmetric property is the definition we used for the subset proofs of set equality. And then the transitive property, if you go from one to another, everything works out. All right. Now we have to start looking at something a little bit specific. Again, I know that you are familiar with some idea of inequalities. You have certainly used inequalities somewhere in the past. But the vague hand-wavy definition of if you draw a number line, the bigger numbers are to the right, the smaller numbers are to the left, isn't quite enough for some of the things that we want to do in this course. So we want to establish a logical meaning for the idea of an inequality on the real numbers. In order to do that, I am going to find a very creative way of splitting the real numbers into a positive and negative branch. The first thing we want to do is make sure that the natural numbers are a subset of the positive real numbers, which makes sense, right? That's kind of how you usually think of positive numbers. And for any element of the real numbers, exactly one of the following is true. This is one of those things that doesn't make a lot of sense in symbols, but when we stop and analyze what it's saying, it should make a lot more sense. Either that thing is a positive real number and its opposite is not a positive real number. That thing is not a positive real number and its opposite is a positive real number, or that thing is zero. All right, so we've established now that every number is either positive or negative. Right? A positive number has an opposite, which is negative. A negative number has an opposite, which is positive. And zero is neither positive nor negative. That's what we're really saying with all of that machinery. And finally, the positive real numbers are closed under addition and multiplication. If you want to add two positive numbers together, the result is positive. If you want to multiply two positive numbers together, the result is positive. It says nothing about what happens with negative numbers, but as long as you start with positive numbers, you stay with positive numbers. Right? We're not establishing an opposite of because that's already shown to be not in here, but we still have closure. All right. So again, symbolically very cumbersome, but should make sense if you stop and think about it. All right. So why did we do this? Well, we'll use that as a way of defining the ordering. I'm going to define that x is less than y if and only if the difference y minus x is a positive number. And then from there, I will define x is less than or equal to y if x is less than y or x is equal to y. And I can define x is greater than y if and only if y is less than x. And I can define x is greater than or equal to y if and only if y is less than x or x is equal to y. So the definition of an ordered field calls for a less than or equal to relationship. So here's our less than or equal to relationship. The other inequalities, just for the sake of completeness. And how do we use that to show that we establish these properties? All right, well, All right, to show the connex property, we need to make one conclusion that we haven't so far that I think is fairly straightforward. If x minus y is equal to 0, then x is equal to y. And if x minus y is, or if x and y are any real numbers, then x minus y must be a real number. And from the definition of the positive real numbers, either x minus y is positive, the opposite of x minus y is positive, which means that y minus x is positive, or x minus y is 0. If x minus y is positive, then that means that y is less than x. If y minus x is positive, that means that x is less than y. And if x minus y is 0, that means that x is equal to y. One of those things must be true. That satisfies the connex property. There's a way of relating any two numbers. I guess that should be since. Second property is the reflexive property. Show that anything is less than or equal to itself. We defined that if x is equal to x, then x is less than or equal to x. That's part of the definition of the less than or equal to operation, or less than or equal to relation, sorry. The anti-symmetric property, let's assume that x is less than or equal to y and y is less than or equal to x. Now, working through similar argument to what we just said with the connex property, if x is less than or equal to y, that means that y minus x is positive, or x is equal to y. And if y is less than or equal to x, that means that x minus y is positive, or x is equal to y. These can't both be true at the same time. All right, a number and its opposite cannot both be positive numbers. That's part of the definition of positive numbers. Right. From the definition of the positive numbers, exactly one of these three things is true. The only choice which gives us both that x is less than or equal to y and y is less than or equal to x is the equals version. And so that gives us the anti-symmetric property. If x is less than or equal to y and y is less than or equal to x, then it must be the case that x is equal to y. It's almost like we chose these definitions just to make sure that the proof was very straightforward. The transitive property is a little bit trickier. For the transitive property, I'm actually not going to quite prove the whole thing for the sake of time. If x is equal to y, or if y is equal to z, then it's a very simple substitution. So let's ignore that and only look at the case of x strictly less than y and y strictly less than z. Well, since x is less than y, that means that y minus x is positive and z minus y is positive. Now, z minus x, using once again the simple trick that we used a couple of times already of introducing something that wasn't there, z minus x is the same thing as z minus y plus y minus x. And so we are adding two positive numbers. Right? This is a positive number, that's a positive number, we're adding them together. One of the parts of the definition of the positive numbers is that it's closed under addition. And so that's enough to give us that x is less than z. And that actually did give us all of our properties. And so to wrap up, I want you to think a little bit about a proof. It's another property of inequalities that you have used extensively in the past, but now that we have this formal definition of what an inequality means, see if you can think of how this proof would work. If x is less than or equal to y, then x plus c is less than or equal to y plus c. To make your life a little bit easier, I'll actually suggest try it without the or equals. If x is strictly less than y, then x plus c is less than y plus c. All right, see what you can do with that problem. See what you can think of as far as how to write that proof out. And I'll see you in the next video.